So Eric Guilyardi is a climate scientist at IPSL in Paris and the University of Reading in the UK. He's an expert in tropical variability and climate change. Eric is also the lead author of the IPCC 5th Assessment Chapter on Model Evaluation, and he co-chairs the CLIVAR research-focused ENSO in a Changing Climate, which turns out to be also the topic of his talk. So welcome, Eric.
Thank you, Kelly. Yeah, thank you for the courageous of you who are, probably totally exhausted after 2 days of really interesting presentation. So I wanted to thank the organizers for inviting me, and also take this opportunity to really, thank RI for being one of the shining lights in our community, and so community. I think it sets an example for many future climate services to come, and also I've taken a lot of interest and advantage in all these exchanges we have from many different expertise. We as climate scientists get a lot of media attention about El Niño at the moment, and very often the questions veer into the impacts and what it means for people, so I don't have many more things to say when I'm interviewed, so thank you for this opportunity. Hopefully we can reciprocate this by the question we'll get is what is happening to El Niño in the changing climate, which is the topic of this presentation. So here I'd like to acknowledge input from Andrew Wittenberg, who's also the other co-chair of that CLIVAR and Solutions Focus Group. Also Mike Fadman, who is here, and Mathieu Langagne, representing the Pacific panel of CLIVAR. Well, Mike is representing Mike, of course. Right, so CLIVAR is one of the 4 groups that are sponsored by WCRP, so the World Climate Research Program, and it has to do with climate and ocean. So the goal of CLIVAR is to observe, simulate, and predict changes in the Earth climate system with a focus on the ocean-atmosphere system, which is at the heart of El Niño, and better understand and predict climate variability and change for the benefit of society and the environment we live in. So that's, you see, the hook with the rest of what RI is doing and we've been discussing. So CLIVAR has been here for a while, and there's a new structure that was started last year by adding to the core panels, which are typical regional panels. I can use the mouse here. Yeah. So the regional panels here of the different ocean basins, which are also join up with an ocean model development panel and an observation panel and a new climate dynamics panel. Join up now with research foci groups, which are seven of those. I won't go into the detail of all those, but just to say that El Niño is present in a number of those, but more specifically, so the Pacific panel region, which historically this is where El Niño has been sitting. But also it's the focus of a new CLIVAR research focus group, and so in a changing climate. And also we'll see a bit in the climate dynamics panel. Right, so that's the more programmatic view of how CLIVAR is addressing El Niño. And so what I'd like to address here is first, understanding ENSO and its underlying processes. We've seen and there are some presentations that already hinted at the complexity of the beast we have to deal with, and its number of underlying processes, so I'll go into that a bit more. Then of course, if we're talking about ENSO, the changing climate or making predictions, we have to rely on models and GCMs, so we have to understand how ENSO is represented with these GCMs, and I'll talk about that. Of course, when we talk about ENSO and climate change, we have to detect a signal of climate change, so we have to understand ENSO diversity and the unforced variations. Then we can go into ENSO the changing climate. And then I'll finish with some of the current challenges we are trying to address in the community. Right, so as you may all know, because I'm sure you're reading all the IPCC reports very carefully, each time there's one that is coming out, there is no change in ENSO mean SST statistics in the future, in the warmer climate. And that's been a recurrent results from the last IPCC reports. These are different ways of looking at it. You can say, okay, I'm going to take pre-industrial control simulations and the 2 times CO2, which are both idealized, but kind of encompassing historical or scenario. And this is the ENSO amplitude. So you see the observation sitting in the middle here. These are different models. And some models have very weak El Niño, this was symmetry, and some have very large El Niño. And you see that in a 2 times CO2, some model will show an increase, some model will show a decrease. But what's the most prominent feature is that the model errors dominate over any signal in the scenario. Same story for semi-5. We don't really see, that's another way of looking at it. You look at basically a PDF of El Niño amplitude, in the control period in blue and a climate change period in red, and we don't really see any evolution of that PDF. Right, so this is the background of what we started a few years back, and we're still there. So to understand El Niño, we look at a number of processes. We heard some already, I'm not going to go into the details, but basically we can categorize them in 3 big families. One is the atmosphere response to SST anomalies. The other is the ocean response to wind or heat flux anomalies. And then there's a number of nonlinear processes. I won't go into the detail, maybe singling out or talking about the westerly wind bursts or those events that we've seen in Michel Laura's presentation yesterday, that they clearly play a role, and a part of the difference between the 2014 La Nada, if we can call it this way, and the 2015 El Niño was really that westerly wind activity. Right, so I'll just illustrate the atmospheric feedback. So we have a positive feedback known as the Bjerknes feedback. It's been known for a while. So if you change your temperature in the East Pacific or Central Pacific, the atmosphere is going to respond to the west of it, and it's going to reduce winds even more, and that's going to reinforce the warming, etc. So it's a positive feedback. So that Bjerknes dynamical feedback is helping El Niño to come about. There's another set of feedbacks from the atmosphere, is the heat flux response, which is usually a negative feedback. That means if you're increasing the SST, this cloud circulation, you name it, radiation is going to come and reduce the heat flux entering the ocean, so it's a negative. Okay? There are a number of ocean feedbacks I won't go into, but we have similar things happening in the ocean. So El Niño, each El Niño event is the balance of all these complicated feedbacks working together. Right, so now how are models doing in that context? This is the amplitude of El Niño. We've seen it already in the previous, but that's compared previous graph. But that's comparing symmetry and semi-5. So again, you have here the observed amplitude, that dashed black line, which is about 0.9. So this is measured as the standard deviation in the Niño East Pacific, the Niño 3 region. So the symmetry are in blue and the semi-5 in red. Here you have modeling centers, so you can see how modeling centers are evolving between their symmetry and semi-5 version, also the diversity that we have. So in symmetry, we've seen there were models with almost no El Niño amplitude, some with twice the amplitude, and that's gone in semi-5, which may think is a good thing. The models are improving. But I'm going to argue in a minute that this is probably not due to some major change in the models, that modelers were looking at this variable. So they will not keep a model version that has either twice the amplitude or no El Niño amplitude. So it's an indirect tuning, if you like. So this is why this criteria that we've been using for a while is that the best one to use to evaluate models. Of course, in terms of El Niño impacts, it's really important to get that right, and the timing and the structure and all this. But in terms of mechanisms, it's not clear. So now if we move to those mechanisms, and here I will just talk about the atmosphere mechanism we've been seeing. So the Bjerknes positive feedback here, the total heat flux negative feedback there. So again, the observation of that dashed line up there, and you see that most models, and irrespective of symmetry or semi-5, are underestimating that Bjerknes feedback by about 30%, which is a lot. That means you're not amplifying, the mechanisms are not strong enough to amplify El Niño, but if you look at the negative feedback, you're also underestimating it by a factor of maybe 2/3 for most models. And of course, if you have not enough positive feedback and not enough negative feedback, what they do, they compensate each other and they give you the right result for the wrong reasons. Okay, so the importance of going at that mechanistic level. Now the heat flux feedback, we can further decompose it in different terms, and the one that dominates clearly is the solar heat flux feedback, so the short wave. And not surprisingly, you see this one not only, so the values are telling us about -7 watts per meter squared per Kelvin, and you can see that the models not only don't get that, but sometimes they even get the wrong sign. Instead of being negative, it becomes positive. And so this diversity, not surprisingly, is due to the clouds and convection, and the way we represent that in the models, we know is a challenge. But this is a way we can track the El Nino errors back to the clouds and convection. So when you're changing your convection scheme or your clouds, you can, looking at those very simple feedbacks, you already have an idea what's going to happen to El Nino in your couple model, when you couple the atmosphere. And the other message here is that we don't see any evolution from symmetry to symmetron. So what, as a community, we're trying to push is people not just look at the linear tree statistics, what we call the performance metrics, but also look at those which are the process-based metrics, are probably more important. Right, so first message, we need to simulate ENSO right for the right reasons. And the linear tree statistics is not enough, it's important as a performance metrics, but as when you're developing a model, you need to move to that process-based metric. Right, now ENSO diversity. So you've probably run across that BAMS paper that came out in last June, led by Antonietta Capotondi. So we all heard that no two El Nino events are alike, they're all different. And understanding this diversity is a real challenge. We have very few observed events, and we've seen there's a delicate balance with all those mechanisms. With those mechanisms are even less well observed, because you have to do in the 3D atmosphere, in the clouds, you have to go into the ocean. So we have a challenge really, and that's a big research question at the moment. So, of course, the question comes naturally is how long do we need to observe El Nino to detect the change, if we are to understand the impact of climate change on El Nino? And for this, I'll take a figure that is actually already behind that wall. You may have seen it. It's an Andrew Wittenberg poster. So that's 2,000 years, so 20th century, of a pre-industrial unforced climate simulation with a GFDL 2.1 model, which is one of the better models of representing El Nino in the symmetry family. And you'll see here that there are centuries where there's very little El Nino activity happening, and centuries where it's very active. And this is just unforced climate. So if you take each of those centuries and do a spectra, you end up with this. So you can see both the amplitude and the frequency. And here each of those is 100-year spectra. So you're thinking, okay, if I want to see a change of El Nino properties in the future, which baseline I'm going to take? I'm going to take, this one or this one? It's really a hard question. And there are other studies that have shown that the minimum length of the simulation needed to distinguish the El Nino amplitude statistically, with a statistically robust number, is several hundred years, 200 to 250 years. So that's a problem for us, because that means that to understand if ENSO has changed, statistics will only help us in 200 years from now, which we need to take decisions. We can't wait to take decisions. So that what we're arguing is that in the meantime we have to rely on physical understanding of the problem. We cannot rely on statistics. That's really so again we have to go from performance to process-based metrics. Right. So if we do that, if we keep the models that, for example, are representing the shortwave heat flux correctly and select those models, then we can start to do some process-based analysis looking in what may happen in the future time. So we've seen there's no change in the mean SST statistics from the same scenarios. If we use a criteria that is process-based, and we're going to look at the extreme El Niños, defined as those where the rainfall is larger than 5 millimeters per day in the East Pacific, so it's really an easy threshold to compute from the models. Now, not all models will produce extreme El Niños. Some will be, locked, not show any variability in the East Pacific. So we only select those that show that exhibit those extreme El Niños. And if you look at those in the historical context, we have one extreme El Nino every 6 events, so maybe one every 30 years. Okay? In the RCP 8.5, so the business as usual scenario, after 2050, what we see is that we have one extreme El Nino every 3 events, so doubling of the frequency. So that's pretty robust statistics because you're using all the 75 simulations here. And what is nice is that we also have a physical explanation, is that to go into a larger El Niño, you need to get rid of strong zonal and meridional barrier, to have the convection move over the cold tongue all the way to the east. That's hard. That's why it doesn't happen very often. 82, 83, 97, 98, and presumably this year as well. Now, if you look at the mean state change in a warmer climate for those models, the cold tongue is warming more than the surrounding Pacific, so that your mean gradient has changed, is weaker. So the barrier to go into extreme El Niño has lowered, so it's easier to go extreme El Niño. Okay. So that's one of the first time we have done, and there's more also on Andrew's poster, just the other side of the wall here. So this is by moving from a SST performance metric to a process-based criteria, we're starting to be able to say things about El Niño in the future. This is the first result, maybe it's probably not the end of the story, it's the first time we can say something about it, so that's really interesting. Right, so as a summary, before I go into the challenges that we're facing now, so really important to simulate the El Niño statistics right for the right reason, via the correct balance of processes. So today I will trust more a model that maybe has a weaker amplitude than observed, but to the right balance of processes, that the model is right on top of observation in terms of the statistics, but through error compensation. This is clearly, in the future we have to rely on the physical understanding. And this is what the second point, so we cannot wait 200 years to know if ENSO has changed due to climate change. So relying on the physical understanding is absolutely key. Right, so some of the challenge that we're facing, that a number of things we need to better understand. I already addressed some of those. So ENSO, diversity and extremes. Can we, what is predictable in terms of extreme, of diversity? The events move along the Pacific, some are more in the East Pacific, some are more in the Central Pacific, some are strong, some are weak. We have to understand if there are predictors to that, or if it's just pure, whatever westerly wind burst we have in the spring will decide the outcome of this. This is one of the research questions we're trying to address. The role of intraseasonal variations, clearly, we know those westerly wind bursts are absolutely key in design, and that's even more so since 2000. I mean, before 2000, the heat recharge of the West Pacific was a pretty safe precursor of El Niño. This is less the case since 2000, and it seems that the role of intraseasonal variations has become stronger. So is this the kind of variability of the system? Some decades are more predictable with the heat content, some decades are less predictable. That's again, these are typical research questions we're trying to address. The role of other oceanic basins. So, well, I would say that the region outside the tropical Pacific, that can involve also the mid-latitudes of the Pacific, or the other basins, do they play a role in triggering El Niño in the Pacific? That's also a research question. It's a hard question because, as we know, El Niño influences those other basins, so distinguishing who is influencing who, or which is influencing which is a hard question. But these are typically the ones we're addressing. Something that came out recently, we're seeing in the models that the atmosphere feedbacks are really dominating the model errors. And there's evidence that in the real system, probably El Niño has been too much of an oceanographer's problem, and the atmosphere probably has a much stronger role that has been thought. So there's a whole new research that is trying to better understand how the atmosphere is playing a role. Obviously, those very simple mu and alpha you saw now, the atmosphere is much more complex than those linear regressions. For example, the Birkness feedback, we understand the Gill response of the atmosphere, but how is the Birkness feedback set up at the weather scale, the intraseasonal scale? These are still hard questions that involve the links between convection, the SST, gradients or maximum, or there are really research questions here. And those questions are part of two community organization, one through the WCRP Grand Challenge on the clouds, convection, and circulation, and one through the CLIVAR Climate Dynamics Panel. So we still have many basic questions to understand really the role of the atmosphere in ENSO. So process-based evaluation of models in ENSO, what we're trying to do also is to provide that computation of those process-based evaluation during the model development phase. Not wait until the model is good for service, oh, but the ENSO mechanisms are terrible. So we need to provide these to the modeling groups while they're developing their model to make sure they're looking at the right metrics. We need observations for that, reliable observations, understanding observation diversity. For example, the wind stress products. Today, the models are within the wind stress observation. There's a large diversity of wind stress product, which is an issue for the models. We don't know which one to trust. So this is a question going to the observational community. Can you understand the differences we have between the different products? We have reached that stage now. For other model problems, the observation are still, well, the models are so far away from observation, so we're fine, but not for wind stress. As Lisa pointed out yesterday, those models have a number of systematic errors, mean systematic errors, like the Colton or ITCZ. They're going to have an impact clearly on El Niño, and we have evidence that if you improve the mean state of those models, you're also improving ENSO, because the mechanisms are the same at the base. It's cloud convection, those kind of things. Paleo records are absolutely key, and this is a big effort of the community trying to interpret and make a synthesis of all these observations we now have in the tropical Pacific from a number of records, like corals, for example. They provide long records and out-of-sample test of models, which is really precious to understand if, in the warmer climate where we have no proxy in the past, the models are still behaving in lack of observation or past observations. Right, and I'll finish talking about observation, which is the base of everything we do in our science. We have to reproduce the observed system. So the Tau Triton array, which is really the backbone of the ENSO observing system, has been instrumental in ENSO progress. I think both it's been a unique resource for models evaluation and process understanding. We talk a lot about ocean reanalysis. The only place where ocean reanalysis agree is the tropical Pacific because of Tau array. This is really important. Many regions of the ocean, those ocean reanalysis don't agree because there's no data. So providing that multi-decadal perspective that Tau is offering us is quite unique. So the TPOS, the Tropical Pacific Observing System, in 2020 is a community endeavor to provide recommendations for the next 20 years of observations. So the discussion is happening now, and I know a number of you are involved, and if some of you want to get involved, get in touch with us. This is really the time to rethink all this. It's a unique opportunity for the community, and I think, like Michael was saying, maybe the funding is not great, but this is probably the time to think really bold. What really do we need as an observing system in the Pacific? We have many things at hand compared to when we started TOGA to really design something that is really ambitious, and we can answer a lot of these questions. This said, we have to be careful not to, can we say in English, put the baby with the water of the bath? I'm sure there's a right expression for this. Yeah, okay. So we have to be really cautious about making fundamental changes to the area as it is now. Having those long time series is essential for providing us understanding those inter-urban variability, and so we have to be really careful about changing all that. So on this, I'll stop here. Thank you.
Well, since we started late, we do have time for questions. So are there any questions from the audience? Yes? Yes? I don't know if there are any microphones, so you might just have to stand up and yell. Go ahead.
I'll yell. Eric, that was very nice. But two things strike me. One is on the rainfall. It's a pretty robust conclusion, both in models and theory and observations, that rainfall will increase in a warmer world because there's more humidity in the air. So when you use that as a metric for ENSO, it makes sense that that will change. And that's important, perhaps, because we care about rainfall. That's what matters for both remote effects, and it is often the remote effect. The other thing, I think, though, is, do you think it matters if it's so difficult to detect a difference between now and in a warmer world? you know, in let's say SST distribution or other measures of ENSO, then maybe it doesn't really matter.
Yeah, I completely agree. And I mean, that's something that clearly came out of this workshop. What I'm taking out is that maybe the SST is not the interesting problem. It's more, you know, and as you said, the rainfall is what's going to affect people. Now, the SST is still a very strong driver of atmospheric circulation, so it's clearly important we, you know, we continue looking at it. But in terms of preparing societies for future El Niño impacts, maybe yeah, you're probably right. That's focusing on the precipitation is probably the one that matters. But that's a much harder problem, as you know. The models are not as good as predicting precipitation than temperature.
One more question? Yes, Lisa?
Does somebody else have a question?
Is there someone else with a question?
Okay. So I really like the process-based approach. And you showed the processes contributing to El Niños today, basically. And so getting El Niños now for the right reason, is great. I think you also want to make sure that you're getting the change in El Niño right for the right reason. So has your group been looking also at any trends or changes in these processes and how between the models and the observations?
Any transients?
The changes or trends in those process measures?
Yeah, we don't really see changes in the process themselves, or we see changes, but they're not robustly statistically.
Like the magnitude of the couplings that you were showing.
Yeah, no, we don't really see big changes, again, because the model's errors are dominating the change. I mean, so I think first we need to reduce those errors to maybe detect a change, but the change might not be so much in the processes, but in the balance of processes. So that's why the decadal timescale is interesting and maybe more tractable for questions to understand those change of mean state that maybe will inform us, okay, if the you know, a 10-year mean state comes more often in the future, then we can maybe say more things about it. So, but typically the nice thing about those process-based is you don't need several hundred years to see a difference between models. 30 years is enough. When you change your cloud scheme, you don't need to run 300 years. Even the 25-year atmospherically simulation is enough to see those changes on changing your cloud scheme or on the Bjerknes feedback or the heat flux feedback.
Great.
Yeah.